All right, I think we can go ahead and get started with this evening. Like, welcome everyone. Good evening. My name is Eleanor Rangers. I'm the president of the Southeastern Pennsylvania Cold War Historical Society. We are celebrating our 15th year of preserving history through the memories of those who created it. And I'd like to welcome everyone to our webinar this evening. I did want to just mention that we will be celebrating America's 250th anniversary in 2026. All the states and federal are working on different celebrations. We do plan on doing something affiliated with the Johnsville Centrifuge and Aerospace Heritage in the Greater Philadelphia region in 2026. So stay tuned for more details. We are, as you can see, a nonprofit affiliate of the Pennsylvania efforts for America 250. And this, of course, is our History in Our Backyard webinar series, which has been ongoing since 2012, along with live events that we also hold at the Johnsville Centrifuge in Warminster, Pennsylvania. As a nonprofit organization, I do have to give the plug every time just to remind folks that if you so desire, we certainly welcome the generosity if you so choose to donate to our organization. For those who have donated in the past, we sincerely thank you. All of those donations are strictly utilized for our preservation efforts. Also, just as a reminder for those who may be new to our programming, we do also maintain a YouTube channel, which is listed under the name of our organization. We do house our lectures that we record here at that site, and I do try to keep that site updated with other Cold War and space race related content. So definitely worth checking it out periodically. We also maintain a Facebook page as well, and you can find us at Southeastern PA, so it's just the abbreviation PA, Cold War Historical Society. We do post our, events there and other Cold War and space race related news as well. So another way to keep up with us as well. This is our listing of our programming for this year, which includes a mix of both webinars and live events. Next month, we have another webinar with a return presenter, Michelle Evans, X-15 historian, who will be speaking about some of her, notes, if you will, about her historical uncoverings regarding the X-15 history. So we're definitely looking forward to that. She is a wealth of information of all things X-15. And then for those of you who are local to the Warminster area, I would encourage you to come to our live program in April with Lou McIntyre, who's going to be talking about TACAMO and also doing a live book signing as well. And then we also have actually our May speaker online this evening, Jim Sobek, who will be live as well in Warminster, and he will be talking about the terminal guidance system on the Tomahawk cruise missile. So looking forward to that. And then, of course, a whole slew of other things to round out the balance of the year. We also likely will be hosting a movie night in March or April. So I will be sending out information about that fairly soon. So more details to come. So without further ado, I'd like to introduce our speakers this evening. First, Steve DiMedio, who is a former RCA engineer located in Camden, New Jersey. And actually, Steve started out working for the Naval Air Development Center in Warminster, Pennsylvania. And I guess you were a co-op. Is that correct, Steve? Co-op with Drexel?
Correct, yes.
Yeah. So he graduated from Drexel University in 1983, and then he took a position with RCA in Camden, New Jersey, and has quite an impressive resume working on high-speed digital tape recorders, solid-state recorders for the EOS and Landsat 7 spacecraft, and other programs included the Mars Optical Disc Recorder and Ground Wave Emergency Network, known as GWEN. He continued to work through all of the RCA successor companies, including GE, Martin Marietta, Lockheed Martin, L3, and L3 Harris, and currently works on high-speed software routines for communication equipment and performs embedded hardware and software development in assembly language, C, C++, and Python. And also in 2019, Steve helped organize his company's Apollo 50th anniversary event to commemorate RCA's contribution to the Apollo lunar program. I did want to put a little plug in about RCA and the Heritage Museum that's based at Rowan University. So I do have the contact information and the website listed there. It looked like it was closed, so it might have been a temporary thing. Maybe it was closed for the winter, but if you're interested in going down to Rowan, if you're local to the greater Philadelphia area, I would certainly, shoot them an email or give them a call to see if and when they will be open. But it looked like they were going to be, it said spring of 2025. So it might have been that they were doing, I think I read something, they were doing renovations or something like that. So, but I did want to make mention of that. And I would also like to introduce our second speaker that we had a delight of Mike reaching out to us actually after seeing this program announced. And we are delighted to have Mike, who is tuning in this evening, actually from the future. It is Friday morning, late morning in Australia, where Mike is based. And Mike was the former director of the Canberra Deep Space Communications Complex in Australia and has a significant tie to the early space program. Mike was born and educated in England, and after graduating in electrical engineering in 1955, he worked in British industry, mainly on aircraft electronics. And then in 1960, he moved to Australia and was responsible for aircraft flight testing instrumentation with the Royal Australian Air Force. Mike then moved to the Canberra Deep Space Tracking Station, and I'm going to probably mispronounce this, in Tidbinbilla, part of, did I get it right? Tidbinbilla?
Yep.
Part of NASA and the Jet Propulsion Laboratory's Deep Space Network in 1966 as Deputy Station Director in charge of operations. And his first mission that he covered was the unmanned mission, the Surveyor missions to the lunar surface. In 1967, he took a similar position at Honeysuckle Creek, one of NASA's three main communications facilities for the Apollo program, and was actively involved in manned missions from Apollo 7 to 13. And then he was involved in the building of a new 210-foot dish at Tidbinbilla. So we went back there, also spent a year at the Jet Propulsion Laboratory in 1972. And that particular antenna supported the Apollo 17 mission to the moon, which of course was the final mission, lunar landing back in the early 1970s. So after a period in Australia's Department of Defense, Mike returned to the Deep Space Station in 1983 and became the director in 1988 and supported missions such as Voyager, Magellan, and Galileo. But the facility also supported the early shuttle program until the TDRS spacecraft were in place for shuttle communications. Mike retired in 1994 on Apollo 11's 25th anniversary. And finally, Mike was awarded 2 public service medals in 1986 and 1995. So between Steve and Mike, we have quite a resume here this evening. And certainly we're going to learn everything we need to know about Apollo surface communications as well as the broader communications network. So we're going to kick things off with Mike. And then we'll turn things over to Steve. One last thing, I did want to put a plug in for a website known as honeysucklecreek.net. This is a wealth of information if you have interest in learning more about Australia's contributions to the larger space program, U.S. space program. So I definitely would encourage you to check that out. Okay, so let's get into it. So Mike, I have, as I said, a number of slides, and whatever you need, I can pull it up for you.
That's a good one to start with.
Okay.
Am I coming through okay?
Yep, very good.
Fine, okay. All right. Well, during Apollo, for most of the missions, I was in charge of operations at, as you just heard, what was called the Honeysuckle Creek Station near Canberra, where I still am. There's me on the right there. I sat at that operations console for most of those missions. This morning, I just happened to be watching an Apollo 8 movie on YouTube. Well worth looking. We were primed for that mission on all the events that went off behind the moon. So we provided the main communications, the so-called Unified S-band system, abbreviated to USB before the current meaning of that acronym. The Unified was that all the telemetry, voice, television, commands, etc., was carried on a single radio frequency in the 2 gigahertz area, and things like telemetry and voice, which Steve will be talking to, found their way onto the downlink, modulating a subcarrier at 1.25 megahertz. So our job was to receive that signal, to receive the main signal, split it up into its parts, and send it off to Houston. And when we did our job properly, which we did most of the time, we were transparent. So when you see Mr. Houston talking, we were a vital part, but a transparent part. You come up with another slide, Eleanor. Yeah, this shows the link. There are 2 discrete links, one from the command module, one from the lunar module. But from the lunar module, when the astronauts were on the surface, there were VHF links, which Steve will talk to. Later on, when they had a rover, there was yet another, effectively spacecraft that again sent down its own television, voice, and TV. Okay, next one, Eleanor.
Oh, hold on here.
Whichever.
Hold on, let me click through.
Yeah,
Oops.
that's.
Sorry, Mike. I'm a little delayed here. Sorry about that.
That's
There we
all
go.
right. That's a good one. That was my operating position. So my job with so-called Ops 1 was our communication term. I generally spoke to Houston, and we configured the incoming circuits so they modulated the transmitter. So I had a bunch of buttons in front of me there. One of which, by the way, allowed me to speak to the astronauts if and when needed. Well, of course, it was never needed, except on 2 occasions. On Apollo 8, we lost a link between Houston and the spacecraft, and I talked to Apollo 8 when it was about 2/3 our way out to the moon. And I only realized fairly recently that I would have held the world's longest distance voice communication record for a few minutes there. And my colleague John next to me, he spoke to the John Young and the other astronauts on the lunar surface on Apollo 16. Next one. Oh, I retired in 94. I successfully got John Young out. John Young, as those of you who've taken any interest in space will know, he really was, well, the most well-known Apollo astronaut. He flew on Gemini, he flew twice on Apollo, and he flew twice on the shuttle, including the very first flight. So I retired and was presented with a retirement model of an antenna by John. Next one. So that was our facility, our station. We were one of three identical facilities around the world. The others were at Madrid, Spain, and one also out in the Mojave Desert, part of the, well, on the same general area as the JPL's Deep Space Network antennas. We also had a deep space antenna connected by microwave link to us here at Honeysuckle Creek. At the microwave tower, you can just about see there, which in general, by the way, had RCA equipment on it. And so I had effectively 2 stations under my operation control. And for Apollo 11, in addition, there was a great big dish 200 miles north of Canberra at the Parkes radio telescope, That's the subject of the movie The Dish, and we receive signals from them as well. So that in general. Oh, and just in passing, I was watching with interest your other slides at the start, Eleanor. I spent 10 years in our defense department, mostly on aircraft electronics, avionics, but also I got involved in the maritime aircraft world, the P3, the P3C. I went around the world when we were selecting a new maritime aircraft after the P3Bs, selected the P3Cs. I also went around the world when Australia was selecting a new fighter aircraft and ended up buying the F-18. So, then I was the manager of a sonobuoy project, what was called the Barra sonobuoy project, which was an Australian designed active system. And I learned all sorts of fascinating information about the whole world of maritime surveillance, which is a 24-hour, 7-day-a-week activity. So that's all for my lead in, Eleanor.
All right. Well, I also want to mention, actually, speaking of P3 and the F-18 and sonobuoys, the Naval Air Development Center in Warminster actually had a pivotal role, particularly with the design and upgrades of the P3 and the P3C in particular. And actually, we do have a former pilot, I believe, on. I think Don Stanton. I think I let him into the webinar. He's a former P3 pilot that flew missions over the Atlantic. So I just wanted to welcome him as well. So that's fascinating.
Right.
A lot of parallels to a lot of the people that participate in our webinars here.
You
So
got a
it's a
P3
delight
TACO
to
on
have you
board
here.
also.
I'm sorry?
Mike A here, a P3 TACO as well.
Oh, thank you.
Don,
I did not know that. So thank you for letting me know.
and Don and I were in the same squadron together.
All right.
Australia made one significant different change to the P3. I gather the sort of master control in the US P3s was down the back, but the Australians, for whatever reason, considered that the man up the front was the one who ran everything. So the master control switch was shifted from the back end of the P3 to the cockpit for the Australian aircraft. They are little useless anecdote.
No. Before we turn things over to Steve, I have one quick question since we have this slide up and I noticed the US flag. So question, were you a US employee when you were working for the Deep Space Network?
No, that's a good point. No, it was a very good Australian-US treaty organized arrangement between the Australian government and the US government. And there was a fair bit of sovereignty came in along the way there. And back in my early days, and I still say this, our arrangement was whereby NASA or its organizations such as JPL or Goddard told us what they'd like done, and we did it, and we told them how much it cost. Those are the arrangements in the early days. But we learned to speak American fairly well, and some Americans learned to speak Australian to some extent. But I had a really good time, very cooperative, no problems in general, except we did have to now and again emphasize that there was a sovereign dimension to our involvement in all of this.
Eleanor, you also want to notice that just to the left and almost directly under the center of the antenna dish is the Australian flag.
Oh,
Yes,
okay. I missed that. I'm sorry. I didn't see it.
And later on, we added a third one. We've added the Spanish one for the sister stations in Spain.
Okay. All right. Well, I think I'm going to go ahead and stop sharing so I can let Steve get online. But Mike, thanks for that very much. And I realize you may have to depart us in a bit, but really thank you for your time. If anyone has
Okay.
any questions for Mike after he leaves, just send them to me and I'll make sure to connect with Mike so we can get them answered for you.
Okay, Eleanor, hopefully I'm sharing now.
Yes, you are.
Okay, so as Eleanor mentioned earlier, this is a presentation about some efforts to recreate the Apollo EVCS AM transmitter. This was the transmitter that brought you voices of the astronauts from the moon. These radios were made right here in the Philadelphia area, Camden, New Jersey, specifically, made by the RCA Corporation, for whom I worked for a little bit right out of college. There's a lot of NASA speak that we need to get through, so just some preliminary terms and definitions. Astronauts wore a backpack on their backs as they walked on the surface of the moon. This was called the PLIS, the Portable Life Support System. And in that PLIS, just at about shoulder level, there was a tray full of electronics called the EVCS, the Extravehicular Communication Subsystem. And this is where all the radio gear was that we'll be talking about tonight. An antenna off the back of the PLIS, and you can tell maybe by the length that we're looking at VHF frequencies here. This photograph is Gene Cernan on the surface of the moon during Apollo 17. Here's some additional photographs of the PLIS with the back covers removed. You can see inside the PLIS all the life support equipment, which is not the subject of this recreation, but this gold-colored horizontal tray here is the EVCS with the radio gear in it. On the right is another similar picture of the PLIS with more of its covers removed. And you can see here the EVCS tray, and here's a top-down view of the EVCS tray. These photographs were sent to me by a man named Dan Shewis, who had a really interesting job. His job was to try on and test out all of the spacesuits of the astronauts before they went on missions. So he has a very cool photo collection of himself wearing all the spacesuits from all the astronauts: Neil Armstrong, Buzz, probably John Young too. Here's an RCA archive photograph of the EVCS tray with its top cover removed. You can see all the radio modules were designed in these little bricks and stacked one next to each other. There are various combinations of transmitters and receivers and audio processing circuits, which we're going to talk about later in the presentation. The radio that we've recreated here, the subject of this recreation project, is this AM transmitter on the left. This is the one that would have brought you the commander's voice from the moon, which would have been, say, Neil Armstrong on Apollo 11. There's also the telemetry unit here on the right, which was made by a Philadelphia company called Sonics. In addition to bringing you the voice information from the astronauts, there was a lot of telemetry that was sent back as well. Astronauts' vitals and the condition of the backpack and things like that, which we'll talk about later. In the lower left here, you'll see the triplexer, which was used to multiplex all of these various radio transmitters and receivers onto the antenna jack and out the top of the backpack. This radio was designed, the radio we're talking about tonight was designed by a man named Jack Yanisov, a legendary RCA engineer. In 2019, I had the honor of meeting Jack as part of our 50th anniversary celebration event for RCA. You can see Jack holding a photograph in his hand, or holding a prototype, that is, in his hand, of one of the radios that he managed to save from the trash bin when the Apollo program was ending. Jack was kind enough to lend me that radio to inspect for a few weeks, and I spent an embarrassingly large amount of time with a loop looking at that radio and trying to come up with a schematic for it because I had not found the actual RCA official schematic at that point. Some of my friends came down with me to meet Jack. This is Tom Anastasia, another friend and engineer, RCA engineer. Here's Jack in the middle, and Fred Barnum, who is our official company historian, who literally wrote a book on the history of the RCA Corporation. So we had a very nice day down there meeting Jack, getting to hear Jack's story, and having him talk to me about these radios was a real high point in my career. So something I'm very happy to have done with Jack. We did bring Jack in for our 50th anniversary celebration at the company. This is Jack being handed an award where we acknowledged his contributions to the Apollo program. This was our company president at the time, and again, Dave Micah and our historian, Fred Barnum. Here's a very interesting photograph from 1968. This is Jack, second on the left here, holding a completed EVCS tray with a bunch of RCA bigwigs. This would have been probably celebrating the completion of the EVCS contract. So here's a diagram similar to the one that Mike showed at the beginning. As he said, there's many radios that were involved in the communications here between the two astronauts. You'll recall there were two astronauts walking on the surface of the moon, the commander and the lunar module pilot. This would have been, say, Neil Armstrong for Apollo 11 and Buzz Aldrin on Apollo 11. They had radio links between them, VHF radio links between them for voice and data. They also had links back to the lunar module as they walked away from it. And the lunar module could, of course, relay information to the astronauts as they went about their EVA. So this was all VHF stuff between the astronauts and the lunar module. And from the lunar module, it was S-band downlink, as Mike mentioned, 2.1 gigahertz or so, back down to Earth. You'll recall that there was a third astronaut orbiting the moon in the command module, who was also in contact at all times. In this case, it was through the S-band link. So quite a bit of radio equipment going at all times to keep communications going between the Earth and the moon and the astronauts. You'll recall in some of the later missions, they included a lunar roving vehicle, a little moon buggy, to allow the astronauts to EVA farther away from the lunar module. In that case, the lunar roving vehicle had another piece of RCA-supplied radio equipment called the LCRU, the Lunar Communications Relay Unit, which had similar radios in it so that the astronauts, since they were out of range of the lunar module, they would instead relay to the lunar roving vehicle, which had its own S-band antenna and could downlink directly to Earth. So, NASA liked its redundancies. So each backpack had multiple transmitters and receivers that allowed for nice features when everything was working, and also some backup features in the event of failure. So we're going to talk about that next. So shown in block diagram form here are the two PLIS backpacks. Shown here is EVCS-1 and EVCS-2. Again, this would have been, say, Neil on Apollo 11 and Buzz on Apollo 11. So the way this worked, you'll see they had our receivers and transmitters labeled R1 and R2, et cetera, here. And the lunar module had a similar complement of receivers and transmitters, again, redundant backups available. So the way this would have worked is Buzz's voice and telemetry data would have been sent over to Neil's backpack via this T3R3 link, which was an FM VHF link. Inside Neil's backpack, it would be summed with Neil's voice and Neil's telemetry data and sent back to the lunar module on Neil's T2 transmitter and received at the lunar module on its R2 receiver. And from there, S-band downlink back to Earth. Meanwhile, Buzz could be listening in on that on his R2 receiver, hearing Neil's voice. So this allowed something that NASA referred to as full conference mode, or what we would call today a full duplex mode, basically a live phone call between the astronauts and the ground at all times without the need for any push to talk. So when ground communicators wanted to talk back to the astronauts, they would relay via S-band uplink to the lunar module, and it would transmit on its T1 transmitter, VHF, and the astronauts could hear mission controllers on their R1 receivers. So again, full duplex communications between both astronauts and the Earth without any push to talk. There were also some backup modes, which we're going to talk about in a minute. But to see how this was controlled, on the front of the astronauts' suits, there was a unit called the remote control unit. There was a mode switch at the top here, which allowed them to select between the primary mode during normal operations and several backup modes. There's also a push-to-talk switch, which was only needed in emergency situations. And this is the RCS unit, the remote control unit, strapped to the front of the astronaut suits. This silver metal clip here that you see along the front was where the Hasselblad camera attached, clamped onto the front of the astronaut spacesuits, which brought us all those iconic photographs from the surface of the moon. On the left here is a shot of that control unit kind of looking down, sort of from the astronaut's point of view. You can see the mode select switch here on the left. So let's talk about the various modes. So in the event of a failure of some kind, for example, let's say the R3 T3 link were to fail for some reason, the astronauts would switch to their primary backup mode, in which case Buzz's voice would be voice and data would be transmitted on his T2 transmitter over to Neil's backpack. And Neil would also be transmitting on his T2 transmitter, and they would both be heard at the R2 receiver on the lunar module. So in this mode, because it's a degraded mode of operation, a failure mode, you did need to use push-to-talk for this. Astronauts would continue to listen to ground controllers being relayed from the lunar module's T1 transmitter to their R1 receivers. And again, in this degraded mode of operation, you did need to use push-to-talk. There's also a secondary backup mode that could accommodate failures, say, in the lunar module. Let's say the T1 transmitter were to fail in the lunar module. They could switch over and astronauts would transmit their voices on their T1 transmitters, again, using push-to-talk, which would be received by the lunar module's still working R1 receiver for downlink to Earth. And uplink from Earth would be relayed from the lunar module's T2 transmitter onto the received by the R2 receivers in the astronauts' backpacks. So you had multiple modes of operation, a lot of redundancy, which was something that would have been very important, of course, for communications on the surface of the moon. So this is the path highlighted here in yellow that we recreated. It was the subject of the recreated. We certainly didn't recreate the entire system here. We recreated the T2 transmitter. This was the AM voice transmitter that would have brought you the commander's voice, say Neil Armstrong's voice and his data. And we simulate the R2 receiver in the LEM using a modern SDR laptop, SDR dongle and a laptop. The transmitter that we recreated is done in the brass board style with period correct components. We'll get into more detail with that later in the presentation. It's running at 259 megahertz. So as I mentioned earlier, the two astronauts' signals from their backpacks are summed together. So for example, the first astronaut, EVCS-1, called here in this diagram, would have his voice spectrum from, say, 300 hertz to 2700 hertz or so, a 5.4 kilohertz telemetry subcarrier with his EKG on it, and a 10.5 kilohertz telemetry subcarrier with the telemetry data for the condition of the backpack. Similarly, the other astronaut had his voice spectrum covering that same 300 to 2700 hertz range or so. His EKG VCO was on 3.9 kilohertz, and his backpack telemetry was on 7.35 kilohertz. So all of this was summed together in the commander's backpack, say Neil's backpack. So the two astronauts' voices and all of their biomedical and PLIS data was all relayed through this one AM transmitter back to the lunar module for downlinking back to Earth. But we don't need to look at my kind of silly diagram there. We can look at the real thing. Here's another shot of the antenna that Mike was talking about, I believe it's an 85-foot dish at Honeysuckle Creek. This is a spectrum analyzer plot here on the left, taken at or near the receiver on that antenna. This was during, I believe it's EVA-3 on Apollo 15. You can pretty clearly see the 4 telemetry subcarriers here that we mentioned. And if you're sharp-eyed, you'll see there's a 5th telemetry subcarrier, and that is from the LaCrue. The Apollo 15 mission included the lunar roving vehicle, and the LaCrue radio unit there on the LRV had its own telemetry subcarrier at about 14 kilohertz. Just an interesting quirk. Presumably, one of the astronauts was speaking here because you can see a lot of voice energy down at the low part of the spectrum. So somebody must have been speaking maybe when this photograph was snapped. So let's talk a little bit about the recreation here. There's some support equipment that's required to run the radio. You'll see in the demonstration that's coming at the end here, we have a demonstrator unit, which is used to support the radio, and we have a telemetry unit, which mimics the sonic telemetry unit commutator that we saw in the EVCS tray with its cover removed. So we use an 18-volt power supply for this project, which is what would have been available in the PLIS. The telemetry was a 30 by 1.5 commutator, solid state commutator, shown conceptually here as a rotating switch. 30 channels of telemetry, 1.5 frames of telemetry per second. So it would sample things like the battery voltage, the battery current, various temperatures and pressures in the PLIS. Since we don't have an actual PLIS here, we're using just the power supply regulator temperature as sort of a stand-in for that kind of stuff. There were also sync levels that were injected to be able to synchronize this stuff when it was received on the ground, so you could decommutate these 30 channels of telemetry. There were also some reference levels which solved an interesting problem, which we'll talk about in a minute. So all this stuff was sequentially commutated and fed into a telemetry VCO, 10.5 kilohertz. And that was summed along with the astronaut's EKG on 5.4 kilohertz from his straps that were biomedical straps that were attached to his chest. All that stuff was summed along with the microphone input from the astronaut's voice after some pre-processing. So all these signals get summed and go in as the audio modulation input to the AM transmitter. And this demonstration unit also applies the DC power to the demonstrator as well. I'm sorry, to the radio as well. This is an example of time division multiplexing. So here's a chart showing all the various telemetry channels that were available in the PLIS. The highlighted yellow ones here are the ones that we've recreated as part of this project. The battery current and battery voltage we mentioned. This water difference temperature, again, since we don't have a real PLIS, I'm using the regulator, the power supply regulator temperature as sort of a stand-in for that. The synchronization, which is identified from the telemetry by being a double pulse width that occupies 2 channels, which is how the synchronization information is differentiated from the normal telemetry data when it's decommutated back on Earth. Interesting to note, these are the channels that things were assigned to. Some channels like PGA pressure were important enough to be assigned to 4 channels. So for the 30 channels. So in addition to getting some redundancy here, if one of the channels were to fail, you also get a higher sample rate on the data because, again, you're sending 1.5 frames of this every second. So some things are getting, 4 samples in every one of those frames. So here's a block diagram of the AM transmitter itself. We start with a 87 megahertz crystal oscillator. And it's tripled up to 259 megahertz with a very clever varactor tripler circuit, which is something I got to learn about as part of this project. It's a very low parts count, very power efficient way to triple from 87 megahertz up to 259 megahertz. That tripler output was fed into the power amplifier and driver transistors. Power amplifier and driver, the driver transistors are 2N3375s, which were one of the rare transistors that could develop any significant power in the mid-1960s at 250 megahertz. So it's kind of working at its extreme edge, but it does manage to get out about half a watt or so. It goes through a RF matching networks, a tunable sort of a pi network. I've added a 30 dB attenuator in here since I'm not authorized to transmit on these frequencies, so we keep it legal by just adding this attenuator and out to an antenna. The audio from the astronauts' mics and those VCOs with all the telemetry information comes in and feeds a pair of audio power amplifiers. This is a really interesting circuit. It uses 2 very early Motorola MC1554 amplifiers, audio amplifiers, little 1-watt audio amplifiers, some of the first such integrated circuits. This would have been about 1965 or 67 or so. Those are used to drive in like push-pull fashion a modulation transformer. And the modulation transformer is connected to the collectors of the power amplifier transistors to achieve the AM modulation. Pretty much all of the components in the recreated radio here are period correct parts of the transistors and all the passives and even the crystal. The Modulation transformer, on the other hand, was completely unobtainable. As far as I can tell, it was a custom piece that was designed by UTC for RCA for this project, so I couldn't find anything close to that. So that turned into a little sub-science project within the larger science project of recreating this radio. We'll talk about that. Here's some photographs of the radio. These are RCA archival photographs. You can see this is a top view of the radio. It's machined out of a block of metal, very nicely machined. Everything's compartmentalized. So on the left here, you see the crystal oscillator circuit. The crystal is this round can here. The middle compartment is the varactor tripler circuit that we talked about a little bit. If you're sharp-eyed, you can see the varactor diode right there. The power amplifier is this L-shaped compartment here. Here's the final transistor, stud-mounted 2N3375 transistor, and the pi matching network that goes out to the antenna here. And in this little compartment in the side is the AM modulation transformer. And if you flip this radio over on its back, very cleverly designed, this back compartment is completely isolated from the other side, so as to minimize interference. So all of the audio processing is on this side. The RF processing is on this side. The audio processing is on this side. Here are the two Motorola 1554 ICs. These are round cans. I believe they're 10 pins. Again, connected in push-pull to run the transformer. These little piston trimmer capacitor adjustment ports come through this side and are used to tune all of the RF circuits on this side with these little very high quality piston trimmer capacitors. So I don't normally show the schematic here, but I'm assuming we have some engineers in the audience that might get a kick out of it. So I'll just go through this very quickly. Here's the 86 megahertz crystal. The tripler circuit is here with the varactor diode. Here are the two MC1554 ICs connected in push-pull to the modulation transformer, and they're connected to the collectors of the driver transistor and the final, and the pi circuit that does the tuning. So I had to dig through the microfilm archive at RCA, what's left of RCA, to find this. It took about 2 years because there's a lot of missing metadata that's missing from the archives. So it was a little bit of a needle in a haystack operation to actually find the official RCA schematic. And I'm such a fan of Jack Yanisov, the designer of this radio, and I was really having trouble finding anything that had his name on it. I found a lot of drawings, but nothing with Jack's name on it. And I'm starting to get worried, but after 2 years or so, I came across this drawing, and when I found it, the first thing I did was look down on the title block, and I saw Jack Yanisov's signature down there from 1968. It was a very satisfying moment for me. I sent Jack a copy of this drawing and a blow-up of his signature like you see here, and he really got a kick out of that. So I like to talk about all of the learning opportunities and the various construction techniques that one learns when you take on a project like this, because that's really we're really in a golden age here for tinkering and for experimenting. So here's a close-up of my brass board reconstructed radio. I tried to follow the same layout as the real radios. So here's my oscillator compartment here on the left. The varactor tripler here is in the middle compartment. The power amplifier is this L-shaped compartment in the real radio, and it's sort of an L-shaped compartment in my brass board. And hiding in the back here is the modulation transformer, which we're going to talk about in a minute. So one of the construction techniques that this project required was this brass board style of construction, which is about the only thing you can do a reasonable prototype job on when you're working at 250 megahertz or so. Another construction technique is a proto board. So these are very common, very inexpensive things to get. They're basically a board, a perf board with lots of holes, and each hole has a little copper ring around it. So you can push component leads through it and solder them together. They're really good at one-off things. So you wouldn't want to make a batch of these, but for one-off prototypes like this is the demonstration unit that you'll see operating the radio. They're very good at low frequency. They're not good at RF, but certainly for the audio preamplifiers and bandpass filters, which is what's on this board. And the power supply that runs the whole radio is another proto board here on this side. So it's yet another construction technique that was needed for this project. It's very low cost and easy to do, especially for one-offs. A really fun aspect here was I said, let me try my hand at some PC boards. When I started my career, the thought of making a PC board for a hobby project was pretty much out of the question based on the cost. But there's free software now and very low cost PC manufacturing houses where you can get these made. So I decided to do the telemetry portion on PC boards just to kind of learn that skill. So this is the commutator, the solid state commutator that rotates around the 30 channels of telemetry. It's modeled after some sonics documents that I found. The VCOs and filters for the EKGs and things are on this board down here. The signal conditioning happens here. This board basically takes all the various telemetry signals and standardizes them 0 to 5 volts, 0 being minimum scale and 5 volts being maximum scale. And the last construction technique is the solderless breadboard. These are very convenient for rapidly prototyping a circuit and doing experiments. You can quickly swap in and out components to change values and make measurements. They're not good at RF. They get pretty unwieldy with anything more complicated than this. It starts to become unreliable. But it is a useful construction technique for doing prototypes before committing to a PC board or a proto board. So let's talk about the transformer, the modulation transformer. As I said, it was pretty much unobtainable. So what I ended up doing was taking a power transformer, a regular DC power transformer that had the same form factor. It's about a 1-inch cube. Taking all the laminations out and pulling the bobbin out and stripping all the windings off and rewinding it to what I assumed would be the modulation transformer specs. I didn't have complete specs for the modulation transformer. I had an RCA source control drawing for it that was used by UTC as part of the contract. It didn't have detailed winding information, but it had some impedance measurements from which I was able to kind of back calculate and infer what the winding might have been. I was also able to examine Jack Yanisov's prototype with a loop to try to gauge or estimate some of the wire gauges and things like that. So it took about 8 or 9 tries or so, but I finally was able to wind this bobbin and mount it into this transformer, pretty much matching the original transmitter used by the RCA radio. So let's see how it did here. On the left is a real Apollo radio that I was fortunate enough to get my hands on an actual Apollo radio to make live measurements for comparison. This purple trace is the RF envelope being AM modulated. The yellow trace is a 1 kilohertz sine wave that's doing the modulation. And you can see it's getting about 85% modulation or so. On the right is the recreation radio, similar waveforms. Again, the RF envelope shown in this purple trace. And the modulating 1 kilohertz signal in yellow. I couldn't resist tweaking the brass board for maximum RF power output, which is not what they would have done with the real Apollo radios. I think they intentionally tuned the real Apollo radios down a little bit less than their full capability, probably just to keep them uniform, astronaut to astronaut, so they didn't have to deal with different levels coming from different backpacks. But I was able to tweak a little bit more RF out of the recreation just for fun. Here's another way to look at the same thing. Any old timers out there will recognize these as modulation trapezoids, which is a way to measure the quality of the AM modulation. Again, the real Apollo radio is here on the left. You're seeing sort of the maximum RF envelope would be on the right-hand side of the trapezoid, and the minimum RF envelope would be on the left-hand side. In a perfect world, these would be perfect triangles. You can see there's some curve here to the original Apollo radio and a little gap at the far end because we're only getting about 85% modulation. But this is more than adequate for voice communications. Here's the recreated radio that shows a similar little bend in the curves and a little bit of a pucker there, which I was never able to get rid of. But again, it's adequate for voice grade communications. So I would never take the attenuator off and walk around Brookside Park where I live about the same distance as the astronauts walked on the surface of the moon just to confirm I had solid copy. It would be unethical for me to do that, so I wouldn't do that. But it's an interesting little scale comparison to see here in those two photographs. So where are these now? You may recall that there were 6 missions that landed on the moon, 2 astronauts each. That's a total of 12 of these radios landing at various points on the surface of the moon to explore different areas. Weight is everything in space flight. So to save weight on the return trips, the plisses were no longer needed. So they were tossed rather unceremoniously out the door of the lunar module and landed on the ground. This photograph on the right is a closeout photograph from Apollo 17. You can see the Bliss laying down here on the surface of the moon. So next time you're out on a warm summer night and you look up at the moon, you can know that there's 12 of these radios laying in the dirt up there, even as we speak. So I like to stress the learning opportunities. When you do a project like this, you learn a lot of stuff. So I learned a lot of RF VHF stuff, which I learned in college, but I never really got a chance to use it in my career. So this was my first real taste in RF and VHF in particular. Got to learn to read something called the Smith chart, which is vital for making RF matching networks to get all the tune circuits working. Transformer design, as I mentioned, we had to kind of build the transformer from scratch. Vector network analyzer was very helpful to help me tune the RF circuits. The simulated ground station was done with modern GNU radio and a software development dongle. So got to read all about that and learn about that, and even design a custom block for the Apollo telemetry decoder. GNU radio comes with a lot of built-in radio blocks that you just drag and drop and make circuits with, but it does not come with an Apollo telemetry decoder, unfortunately. So that's an opportunity to do a custom Python block. We'll see a little bit of that in the demonstration at the end. KiCad schematic software capture and PCB routing. KiCad, for those of you that don't know it, is a freely available open source schematic capture and PCB routing tool. It's capable of professional level work. I mean, people make a career out of schematic capture and PCB routing. You can learn it for free by just downloading this and capturing some schematics and making some PC boards. That's how I made the boards for this program. So you could learn a whole skill here just from your hobby experimenting. So my main point here on this slide is that this is really a golden age for experimenting and learning. You have free and or very inexpensive software, hardware, tools, and test equipment. It's really a golden age for experimenting and tinkering. Just to drive that point home, when I started my career, we had these Hewlett-Packard vector network analyzers, which were marvelous tools. These would have cost maybe a year of my salary in 1983, so I could never, hope to own one of these, especially for a hobby job. But for this Apollo program reconstruction, I was able to buy this little handheld vector network analyzer for $50 or so on Amazon. It's probably not up quite to the same specs as the Hewlett-Packard, but it's more than enough to do a project like this. You can see me tuning a filter or something here on this capture. Here's some screenshots of the KiCad schematic capture tool. This is from their website. Full-fledged multi-layer PCB layout and routing. Makes beautiful Gerber files that you can send out to any PCB house and have them make the PC boards. You put your credit card in, it's $2 a board. A week later, the boards arrive at your mailbox. So it's really very low cost to make and design these electronic elements now. Here's a screenshot of the GNU radio program, which again is free open source. You can drag and drop all these blocks on the right here. These various components can be drag and dropped and connected, and you can right click on these and set their parameters and make whatever you want. In my case, I made a AM receiver and a telemetry decoder to act as the ground station, a simulated ground station for this AM radio. Very easy to use, and it's free for anyone to download. So we've been talking about the communications radios, but I'd like to point out briefly some of the other contributions that RCA made to the lunar program. On the upper right here, you can see the Saturn V launch computer. This was the computer that was used to sequence the starting of the Saturn V engines. When you hear the NASA Public Affairs Officer Jack King say ignition sequence start during the countdown, this is what he's talking about. This computer is firing up and sequencing all the various pumps and valves and everything else that it takes to get a Saturn V lit up. This next photograph down is something Mike is probably familiar with. The TV that came back from the moon was not compatible with broadcast TV in our homes. It was a slow scan, I believe 10 frames per second. So RCA made this scan converter, which would convert that slow scan TV into NTSC TV so that it could be viewed on our homes around the world. It's also a lunar sounder. Another project that Jack Yanisov worked on was like a ground penetrating radar that flew over the surface of the moon and looked for water. You have probably all seen these pictures of the lunar roving vehicle with its S-band antenna pointing back at Earth and its television camera that brought us those beautiful views. And here's the LaCrew with its cover flap down. But you've probably not seen it like this. Here's the same equipment on the workbench at an RCA lab, probably RCA Princeton. Here's the antenna in its up position, the LaCrew with the VHF radios in it, and the television camera, which was ground controllable to point and focus in different areas. So RCA really made quite a contribution, quite a bit of hardware for the moon landing. I always like to thank some of the people who were very helpful for this project for me. Dave Kumpf and Deb Brooks-Mantle back at L3 Harris gave me some access to the microfilm archive. Dave O'Rourke was kind enough to lend me some live Apollo radios to make live measurements on, which is extremely helpful when you're trying to recreate something like this from so long ago. Fred Barnum and Michelle LeBrake, who are our historian and photographer, they have access to hundreds of thousands of photographs that are now down at the Hagley Museum and available for research. I have to give proper honors to Jack Yanisov for designing these radios that brought voices from the moon. Sam Petrofita, another legendary RCA engineer who designed the command module radios. Had a nice conversation with him on the phone where he told me the story of that. These were really some of the great engineers from that era. Conrad Haber, who worked on the LaCrew, I believe on the VHF portion of the LaCrew as well. So here's some references if anybody wants to do some more reading on this. This first one is an interesting PDF by John Dilks. This is what brought me my attention to Jack Yanisov and his story. It's a very readable 2-page story of Jack and his radio and how he came to be working at RCA. Okay, so we're about ready for the demo. Normally, when I make this presentation, I do a live demo, but we wanted the folks on the live stream to be able to participate. So in this case, we've pre-recorded a video demo. But here's what you're going to see. We have a microphone that goes into the demonstration unit and the EKG signals in the telemetry unit as well. These two units talk to one another, and all that information is fed into the transmitter. Again, we have a 30 dB attenuator since we're just transmitting across the room. We go through an antenna to our modern SDR dongle, which is connected to a laptop running the GNU radio software decoder to simulate our ground station. So with that, I think I'm going to stop sharing and Eleanor can play the video. The video runs about 5 minutes, I think.
All right, sounds good. All right, let's see. Media player, share sound.
This is a demonstration of the Apollo EVCS AM transmitter set up in its demonstration mode. Let's take a look at the equipment we have set up for the demonstration. On the left, you'll see the PC, which is running the application software. This acts as the receiving ground station and decodes the AM voice data from the radio along with the telemetry. On the PC's left side, you can see the SDR dongle that's acting as the receiver. It looks like a little USB device sticking out of the side of the computer, and its antenna is pointing down. In the center, we have the demonstration unit, which supplies power and audio processing, and below that is the telemetry unit. That's the thin aluminum case you see on the bottom. In front of that, on the left, we have the EKG signal conditioner, which transforms EKG signals into something that can be sent by the telemetry. In the back, we have the demonstration radio. This is the recreated Apollo EVCS radio. You can see it's in brass board construction style, which is how a lot of the engineering prototypes would have been made back in the day. On the far right is the antenna, which is separated by a little bit here so as to not produce too much interference. We're operating the radio in very close surroundings at the moment. We also have some extra equipment here along the front, a microphone on the left, along with some audio recordings that I have set up on a phone so we can play them back into the radio for demonstration purposes. So I've turned the radio on now. You can see the telemetry unit lights are on. At the bottom left is the green power light, and in the center there's a flashing yellow light. All good projects have at least one flashing light, and this one is indicating each frame of telemetry as it's sent. It sends about 1.5 frames of telemetry every second. So I'm speaking into the microphone now, and you can hear the audio as it's being received by our simulated ground station. There's some latency here. That's a byproduct of the modern SDR receiver we're using. You know, it's interesting to think about the modern technology having that limitation, introducing latency that the old analog technology of the 1960s would not have introduced. That can be fixed, but it's an entirely separate project. Okay, so here we have a close-up look of the receiver software in action. This is the software application that processes the data coming from the SDR dongle. In the upper left, you can see the audio spectrum coming in off the radio, and you can see the telemetry subcarriers here at about 5 kilohertz or so, and the 10 kilohertz telemetry subcarrier, which has the twin peaks that are characteristic of a biphase type signal. Below that, you can see the telemetry being decoded. Here is the battery voltage on the left, running about 18 volts now, which is typical for this radio and the power supply that I'm using. The battery current is shown here after being decoded, and the regulator temperature on the power supply is running about 41 degrees centigrade right now. And below that, on the large waveform display here, is the raw telemetry information. You can see the sync pulses going negative here, the calibration pulses going from min to max, and the various telemetry channels in the middle being decoded. Again, this is pulse amplitude modulation being decoded. And I couldn't resist connecting some electrodes up to myself here, so we're looking at my live EKG here being transmitted by the radio in this upper right panel. So that was another interesting learning opportunity for this project. Got to learn a little bit about EKGs and how to read the waveforms. This is how the astronauts' hearts were monitored while they walked on the surface of the moon. And you might remember flight controllers talking about astronauts' heart rates reaching a certain level under periods of stress, like during the moon landing itself. And this is how they determined that. They had live EKG data coming back from the astronauts pretty much at all times when they were suited up. One interesting aspect of this radio, since it was intended to pass telemetry in addition to voice, the input bandwidth is all the way up to 10 kilohertz. That is, there's no filter on the audio input. So it's actually capable of sending some pretty hi-fi audio, which was certainly not the intention, but it is one of the quirky byproducts of the design of this radio. So just for fun, to demonstrate that, I can play some music through the radio and we can hear the sound quality. So that's not too bad for 5 transistors, and I couldn't resist putting this next piece of audio in.
I'm going to step off the limb now. It's one small step for man, one giant leap for mankind.
So I hope you get the significance of that. That's Neil Armstrong's voice, once again flowing through this same circuit that brought us his voice from the moon in 1969. So we can conclude here with a view of the real Apollo radio. This is the radio that the demonstration unit was modeled after. You can see it fits in the palm of a hand. This particular unit has no covers, so you can see all of the various chambers and components that are in there. It's really a marvel of mid-1960s miniaturization. The RCA wiremen who built these things back in the 1960s were really very skilled craftsmen. You can see the RCA logo and assembly numbers and drawing numbers on the side of this particular unit. So radios like this brought you Neil Armstrong's voice from the moon along with the other astronauts too. Thank you very much for listening.
Steve, can you hear me?
Yes, I can.
I'm out in Indianapolis, and I have a question about why the connection didn't go up to the module that I guess wasn't the lunar scourger. What's the unit called that's in orbit around the moon?
The command service module.
Why did they not go up to the command service module, which probably had more power capacity, and then to Earth from there? Is that because it was in orbit around the moon and sometimes would not be visible by Earth?
Yeah, that's correct. Most of the time it was behind the moon and out of range of the lunar module on the surface, and often out of range of Earth itself.
Okay. What orbit was it in? Was it equatorial, or I don't understand the orbital dynamics for going around the moon.
Yeah, I don't know the orbit either. I believe it's probably pretty close to equatorial because all of the missions kind of landed into the sun and near the equator of the moon. So my guess would be an equatorial or near equatorial orbit, but I don't know that for sure.
I see Mike nodding.
Ah,
Mike, you're on mute. I think the orbits were pretty circular around the moon too.
yeah, I believe that's true, Eleanor.
Steve, I got a question for you. How close to the actual manufacturing of the radios did you get?
So I was not there at all. So I unfortunately joined RCA maybe 15 years or so after the Apollo program ended. So this is all sort of historical for me. I was 9 years old when the astronauts walked on the surface of the moon, and I admired those men very much. But what I was really fascinated by was the hardware. I wanted to know how the rockets worked, how the radios worked, how the computers worked. So when I came to work for RCA years later, after the Apollo program had ended, I was pleasantly surprised to find out that those radios were made 2 floors above me, where my desk was. Unfortunately, it's quite a few years before I got there. So I did not participate myself in the design of these radios, but hearing Jack Yanisov's story and another gentleman named Mike Weber, who was involved in the assembly and the testing of these things, which were apparently very difficult to assemble because they're so miniaturized. That's where a lot of this background information comes from.
I have a little side note for you then. Years ago, we moved here. I was at Naval War Warfare Center, Warminster. We took a dog from a woman in New Jersey, the breeder, Pat Detmold. And she told me a story one day back in the 60s. She worked for a company that did a lot of assembling of circuit boards and small equipment. And she had, for their dexterity, I guess, and they never told her what she was doing. And after Apollo 11 landed on the moon, they had a meeting with all the people that assembled the radios and said to them, now we can tell you what you were doing. You were building the radios going to the moon.
Wow.
So she was one of the assemblers that puts this stuff together.
Well, if you have any information on that, I would like to hear it because I'm trying to gather as much information on the history of these radios as possible. So to meet someone who had actually assembled one would be very interesting to me.
She passed away a few years ago, but I was amazed when she told me that story. And they worked in the blind, so it was all compartmentalized what they were doing. They didn't even tell them what they were working on.
Interesting.
Wow. I know we have a couple of questions actually in the chat that I just wanted to throw out there. I think this was kind of answered already, but was the same type of radio used for all Apollo missions? And I believe the answer is yes, but I just want to confirm that.
Yeah, as far as I know, all of the Plisses had the same EVCS trays in them. You can tell by the serial numbers that quite a few of these were made. As far as I know, there were no significant changes in the later missions. The command modules all had the same VHF equipment in them as well. I don't believe there was any changes to the S-band stuff that Mike was talking about either. There might have been minor tweaks here and there, but basically it was the same radios throughout the entire Apollo program.
Okay.
It was the same radio. Am I coming through?
Yeah, you're coming through now. Yep.
Oh, good. Yeah, same radio. But as you showed in your presentation, Steve, the addition of the LCRU, or the Moon Rover, that added another spacecraft, basically. And just in passing, your mention about EKGs reminds me that on Apollo 11, we were the first to receive the television here. But the thing that worried me at the time, we had an intermittent EKG signal. And my worry at the time, and I try and tell the media this, but they're not the least bit interested. I was more concerned about the intermittent EKG than I was about the television. There you go. That's all.
Let's see. Oh, question. What other radio manufacturers competed with RCA for the contract for these radios? Any idea?
Yeah, so RCA in those days was a big competitor with Collins. And if I can take a minute to tell a story that Sam Petrofita told me, when they were redesigning the radio, when NASA was redesigning the radios, or I should say the command modules after the Apollo 1 fire, it was a complete redesign. So RCA and Collins were out at North American Aviation in California, who was the prime for the command module. And they had to pass these tests where they had tape recordings of various words, and you had to score certain high scores on intelligibility of the words. And that was how the competition was going to go between RCA and Collins. But the RCA radio used something called infinitely clipped speech, which was something that Sam Petrofita had come up with. And it sounded so good, apparently, that the Collins engineers thought the RCA engineers were cheating and had run wires back and forth and were not using the radios at all. That's how much better the RCA radios sounded than the Collins radios. So RCA won the contract for the command module radios as well, largely due to this infinitely clipped speech approach that they had used, that I think was developed by Sam Petrofita. So when I found Sam's signature on his drawing for the command module radios with the infinitely clipped speech, I sent him a copy of that, and he was very appreciative of that too.
Very interesting. Another question, how long did it take for the audio RF to get from the moon to the Earth and vice versa? And then I have an additional question to tack onto that. I want to talk a little bit about Quindar tones and how that all came about. The beeps that we always hear, the iconic beeps from the Apollo communications.
Yeah, so the downlink time, Mike would probably know this better than me. I believe it was about a second or so to get from the moon back down to the Earth, which made it.
And not only the time from the moon to the Earth, but then landlines and then satellites across the Pacific and into Houston and then out and around the world. On Apollo 12, I have the theory that they burnt the camera out because of these delays. We were tracking at the time, and we're watching him moving the camera about in Apollo 12. And I said, he's going to point it at the sun. And they were doing this up a bit, down a bit. And I think they got out of sync between Houston and the astronaut Albin because of the radio delay. Oh, and the other thing that came into the radio delay was the filming or taking pictures of the lunar module taking off from the moon. My friend Ed Fendell, who was in charge of all the comms at Houston, I sat in with him on Apollo 17. I happened to be there. And he tried to take the video of the liftoff on 16, but hadn't quite made it accurate. So there were all sorts of delays involved, not only the RF delays, but the computing and command delays. But Ed Fendell, who, by the way, was notorious for saying there should not be any TV on Apollo, but in the end, he got a special award in Europe for being captain video, and his major achievement at the end was getting the TV camera to track the liftoff from the moon. That's all.
Interesting.
What
about Quindar tones? Can either of you comment on the adoption of that and the use of them?
They were part of the space biz right from the beginning. And in fact, I was amused to hear them not long ago in the space station usage, which astounded me. There was a beep of, I think it was 2.1 kilohertz, something like that, to turn on a relay, and a second beep at just a slightly different frequency, about 100 hertz difference, to turn it off. And that, of course, was to stop any interference. That was triggered by the Capcom's microphone switch. Therefore, even if anybody got onto the air-ground circuit, they didn't go up to the astronauts because only the Capcom had the Quindar button. Although I could key it as well. Now and again, the Quindar wouldn't perform completely, and we had to keep literally an ear on that. and key the transmitter if and when it was needed. But it's astounding that there appears to be still in use somewhere in the system. That's all.
Another question, what was the output power of the actual units?
So the VHF unit that I modeled here is about half a watt. It can go up to about 750 if you push it, 750 milliwatts. But I think its design spec was about 500 milliwatts, which was more than adequate just to go line of sight back to the lunar module a quarter of a mile or so.
And I think the S-band power was something like 20 watts or thereabouts.
That sounds about right.
But we had real good, big, positive comm margins. I mean, compared, say, with Voyager, which is now, about 16 light hours away, and still having a signal receivable on Earth, we really had no problems. Except on Apollo 13, where they turned down all the things that they could turn off, and we had a very weak signal to deal with there. But other than that, we never had any problem with S-band power. On the uplink, we were radiating 20 kilowatts into a third of a degree beam width. So again, uplink margins were no problem.
That's great.
Actually, one of the participants here on the webinar noted that on chat that Wikipedia actually has a good description of Quindar tones for ground network switching. So if anyone has interest, I guess you can look up Quindar tones, and there's a good page for reference.
And there's also some on our website as well.
All right. And that is, again, honeysucklecreek.net for any of you that may be interested in checking that out. Okay. Any other questions?
Yeah, this is Jim Somek again. I have one more. The 85-foot antenna at Honeysuckle Creek, did its beam width essentially cover the entire moon, or was it narrow enough focus that you had to point it where you knew the astronauts were?
That's a good question. The beam width at S-band was about 0.3 of a degree, and the moon is about 0.5 of a degree. And that's really partly why we had two antennas, the one at Honeysuckle Creek and one at Tidbinbilla. So when we were tracking, we'd have one antenna on one spacecraft and one antenna on the other. We could get a usable signal, mind you, through both onto a single antenna, but with the luxury of two antennas, it wasn't an issue. That's at S-band, mind you. Nowadays, S-band isn't used very much. Up in the X-band, 8 gigahertz, and beam width there does start to become pretty significant.
Okay.
Was there any attempt to merge those two signals to do a phase shift so that you could add them?
Well, we were receiving them both at the same time through the front end with discrete phase lock loop receivers. I had 4 receivers at Honeysuckle and 4 receivers at Tidbinbilla. Any of each could be configured for the downlink. As well, by the way, we'd forgotten to mention these ALSEP, Apollo lunar something experimental. They were
ALSEP, ALSCP, right?
That's right. The seismometers and the like that were left by the astronauts, they radiated yet again on another frequency. Although that signal was strong enough to be picked up by some of our 9-meter network stations, places like Hawaii and Guam and Carnarvon. There was about 20 near Earth orbit stations in the manned flight network, and the ALSEP activity generally could be offloaded onto those antennas, those stations.
Thanks.
Great. Well, I've gotten a lot of kudos this evening in the chat for folks online, including us radio geeks really enjoyed it. So,
I think Steve and company have done a fantastic job there. It's marvelous for someone to take an interest in the archival the archive business really needs a lot of thought, certainly in the space biz and probably in others. We put in a great deal of effort trying to find the original videotapes of the first step on the moon. And a lot of other people got involved at Goddard Space Flight Center in Houston, and they went through all sorts of magnetic tape archives but never ever found the original ones, from which the quality of the video would have been very good. Although RCA had this video converter at Honeysuckle, it was literally crude. The slow scan picture was put up on a CRT, and a camera was pointed at that to convert it into NTSC. And a great deal of quality was lost just in that conversion. And if you go to our website, you'll see some Polaroid pictures taken by the scan operator of the quality on the screen before it was converted, and far, far better than what has been received. So archival, if anybody on this thing is involved in any business of doing something novel, new, or different, please find some sort of archival process somewhere. That's all.
It looks like we have one additional question. This is a question for Steve. Is the GNU radio GRC file available for download? I work with GNU radios quite a bit.
It is not. I could probably make it so. Maybe I can forward it to you, Eleanor, and you can post it somewhere.
I can do that, or I don't know, Jim Elmore. I don't know if you can come on audio. I can connect you to Steve after the call. All right. Well, we'll follow up on that.
Yeah.
Okay. All right. Any additional questions before we sign off for this evening?
I have one final one. Steve,
Sure.
whatever triggered you to do this project in the first place?
Well, I think it was meeting Jack and hearing his story, and being fascinated with radios since I was a little boy, and have tinkered with radios over the years. But this would have been sort of a crowning achievement and a nice sort of bookend to my career. So that's why I decided to do it. It took about 2 years of hobby time to put that all together, and it's been a real honor to meet Mike as part of this effort and hear his story. And he added a lot of nice value to the presentation. So I enjoyed that too as well.
Thank you for doing it.
Thank you.
All right. Well, this was fascinating. And again, Steve, thanks. I'm glad we were going to do this last year, but I know we had to delay.
Yeah.
But really appreciate you being available for this for 2025. And Mike, thanks for finding us. And this was definitely a real bonus for us.
Yeah, definitely.
Okay. All right. Well, again, I want to wish everybody a good evening. And remember, we have another webinar coming up in March about the X15. So hope you'll be able to join us for that in March. So with that, I'm going to go ahead and conclude for this evening. Thanks again, everyone, for your support. And we will see you soon.
Thank you.
All right. Bye-bye.
Bye.